Hey everyone, this is lesson 941 on inverse functions. At this point in time, we've kind of already seen our inverse functions. Even though lately we've been spending a lot of time on regular functions, quadratic functions, absolute value, square root, exponential, reciprocal. We have seen a number of functions. There are many functions. And when we talk about functions, there's actually an inverse function that's associated with that function. So we've technically already seen this before. Some prior knowledge that you should be thinking of is our trig ratios. So the couple things to point out about our trig ratios is that when we were using our sine, cosine, tangent, we would always give it an angle, some degree, and the outputs, right, we'd give the trig ratios like sine, we'd give it a measurement of the angle, and it would give us as an output, it would give us the ratio. So same thing with cosine and tangent. All we would need to do is give it the angle, and it would give us a ratio. Now, the inverse trig ratio worked the opposite. We would give it a ratio, that would be considered the input, and the output would be the angle measurement. So that's one thing to think about. The other is the actual notation. If you remember, they look almost the same, right? We would use the same name, tan for tangent, cosine, sine, except with the inverse trig ratios, we would have this little -1, kind of looks like an exponent, which is really an indicator of an inverse function. And so, which ties in kind of to an official definition given to us in our book that says the inverse function written, just see how it's written, with instead of f of x, it's f of, with this little -1 at the top like an exponent. What an inverse function does is it actually undoes an output and recreates the original input. So that's what we're going to look at today, is how can we better understand an inverse function, and how can we write them, and how are they related to the original function. So let's look closely at specifically this function, or function machine. Sometimes we refer to functions as function machines. Kind of like a vending machine. It's designed to work a certain way, right? You give it money, it gives you whatever you're trying to purchase. So maybe like a drink or some food item. So in order for it to work properly, it needs to follow certain procedures. So in this case, this function machine that I have here, if we give it a number 3, it's going to do some calculations, it's going to do a number of steps, and eventually it's going to output a 13. All right, so that's how a function machine works. So we have an input. In this case, the input is 3, and our output is 13. Now, when we look at the inverse function machine, what's happening here is you'll notice at the top there's a 13. Well, the 13 was the output. So the reality is that this output now becomes the input, and once that machine does its calculations, the inverse function machine, now it's going to do things in the reverse order. So all those steps that the original machine was doing, the inverse function machine is going to do them in reverse order. And so, which will end up resulting in this 3, which is now the output. All right. Well, you'll notice that output was the same as the original input, which is what should happen, right? So if I give you $3 and you give me, let's say, some fries, and I say, you know what, I changed my mind, here's your fries back, I would expect for me to get my money back, the $3. So even exchange. So this is the general idea of how an inverse function works. So let's look at more specifics, the more specifics of a function machine and how it might be working. So on this problem, we have this function machine that is taking the value of 3, and this function machine is called g of x. That's how there's the notation g of x, and we do not know what the output is. So we're going to look at calculating that. But we do know is what all the steps that machine is supposed to follow. So according to this list of steps, it says it's going to take that number, it's going to multiply it by 5, it's going to subtract 8, and then it's going to divide by 2. All right, so that's how this machine is supposed to work. And so what we're going to do is let's actually write an equation that does all those steps. All right, you could probably do those calculations in your head one at a time, but it'd be nice if we actually had just one equation that combined all those steps in one. All right, so let's start with the notation. So we have g of x, which represents that function machine. Now, what I'm going to start with is, since we are using x, we're going to look at the first step, and the first step says to multiply by 5. So that means whatever number I have, I'm going to multiply it by 5. So x, if I plug in an x, I'm going to multiply it by 5. So now I have a 5x. Second step says to subtract 8. So whatever the answer that gives me, I'm going to subtract 8. Next step is to divide by 2. So I'm going to take that whole thing and I'm going to divide it by 2. All right, so what we've just done is we've written an equation for this function machine, g of x. Now, if we want to actually calculate it, right, you could probably even do some of these calculations in your head. If you haven't already calculated it, you might want to try to do that in your head really quick. Take 3, multiply it by 5, subtract 8, and then divide by 2, and think about what number that might give you. So what we're going to do is actually test it out. Right? Hopefully you did those calculations, and let's see if you get this correct. So if we want to show what this might be, we're going to use that equation, and what I'm going to do is I'm going to, instead of plugging in an x, I'm going to plug in a 3. So this represents the input. So 3 is our input. I want to know what the output is, so I'm going to rewrite this, except instead of that x, I'm going to plug in my input, right? Because it says we're going to plug in a 3. Okay, so let's plug in a 3 then. So let's put our 3. All right, and if we simplify this, 5 times 3, oops, let me rewrite this, g of 3, 5 times 3, right, is 15, and 15 minus 8, I'll do this in steps, so 15 minus 8 divided by 2. So now we could take it a step further, and we're going to be left with, let's see if I could fit this. So this is going to be, what, 7 divided by 2? All right, so that means that our g of 3, when we plug in a 3, we're going to end up with 3.5. All right, so keep in mind this 3 is our input, and this 3.5 is our output. All right, so okay, that's how our function machine is working. Now let's write the inverse function machine. So if we do this correctly, when we plug in a 3.5, we should end up with a 3 in return. So what does that equation look like? All right, so you should notice I have the steps already set up for us. We're going to write them out. So steps of an inverse function. So how does this work? Well, we're going to take the very last step of our function machine, which in this case is divide by 2. And what the inverse does is it takes that step and it's going to undo it. So it's going to undo. And what I mean by undo is not only does it so not only are we going to do this last step first, but it's going to undo that division that it was doing initially. So that what's the opposite of dividing? The opposite of dividing for us is going to be multiplying. So I'm going to zoom into this. So we're going to multiply by 2. All right, and then what comes next is we're going to do maybe this step in the middle. And this is also going to undo. So subtracting by 8, the opposite of subtracting by 8 is going to be, we're going to add by 8. And then the last step for us is going to be the opposite of multiplying by 5 is going to be divide by 5. All right, so all I did was reverse the order, and every operation is going to do the opposite. So now we have an order for our inverse function. So now let's use that to help us actually write the equation. So let's start with the notation g of x, inverse g of x. Don't forget that minus 1. And we're going to start with the x. So I always like to just write the x first. And the first step said to multiply by 2. Okay, so we're going to put a 2 in front, 2 times x. And then we're going to add by 8. So I'm going to put a plus 8. And then the last step is to divide by 5. So now I'm going to divide by 5. All right. So now we have our equation. And so what we would need to do is to test this out and see if it actually gives us the answer that we want. So like I said earlier, if we plug in a 3.5, we should end up with a 3. Okay, so let's show that. So I'm going to plug in our 3.5, so 3.5, which means instead of x, 2 times x plus 8 divided by 5, I'm going to put a 3.5, and now I have something to simplify. All right, so 2 times 3.5, what does that give us if we multiply 2 times 3.5? So if you're not sure, use a calculator. So that should give us 7 plus 8 divided by 5. All right, so now what we're left with is 7 plus 5 is 15, and 15 divided by 5 gives us our 3. All right, so now if you notice, oops, this is our input, and here's our output. And you'll notice, right? Input and output match, right? They're the opposites. So the input of 3 now becomes the output of 3, and the output of 3.5 was the input 3.5. All right, so this means we've written an inverse function correctly. All right, so this is a process, right? We could list out all the steps. If we know all the steps, then we should be able to rewrite them. So maybe you're not going to be given these steps, but what if I give you this equation? If I give you this equation, can you write the inverse function? Well, all you would have to do is just write out all the steps, reverse the order of everything, and then once you have these, you could easily write your new equation. It's not difficult, but it would take some time. So we need a little bit of an easier approach, so that's what we're going to look at next. All right, so writing an inverse function. So we're going to practice 2 of these on this problem. So let me, I think there. All right, so here we have this function, n of x is equal to 4x minus 12. And this is what we call function notation. So in case you're not sure why I have function notation in there, anytime it's written like this with n of x, now this would be like the equivalent if I say y equals to, right? We're used to seeing y equals. When it's written like this is what we call function notation. It means it's showing us what we're actually plugging in as input. All right, so it becomes very difficult to convert this to an inverse function when it's in function notation. So to make it a little bit easier for us, it might benefit us to change this to an equation notation. All right, and so when I talk about equation notation, what I mean is, let me zoom into this. So this arrow here means I'm going to change it to an equation notation. And all that means is I'm going to replace that n of x with y equals. So now instead of n of x equals to 4x minus 12, I'm going to write y equals 4x minus 12. All right, hopefully that seems easy enough. We're just rewriting it. And the reason why we're doing that is so we can make an easy change and get an inverse function. So what I mean by that is if you didn't already notice, when we did the previous problem, the input and the output got swapped, right? Input became output. Output became input. So in this equation, what letter represents the input and what letter represents the output? So since x and y represent input and output, what happens if we just swap those in the equation? All right, so what I'm going to do, I'm going to go over here. So at this point, I'm just going to swap my x and y. So that means instead of y equals, I'm going to have x equals to 4y minus 12. All right, easy step. First, I wrote it as an equation, and now I just switched the x and the y. That's all I did. So technically what we've just done is we've written an inverse function just by swapping the x and y. The only problem is it's not in the proper notation. All right, so what we need to do at this point is we're going to solve for y. We need to get it back so it looks like an equation equal to y. All right, so let's work through this. So I'm going to start by adding 12 to both sides. And then that's going to give us x plus 12 is equal to 4y. And then to get rid of that 4, we're going to divide both sides by 4. And the result is going to give us x plus y over 4 is equal to y. All right, so what we just did, right, what we just did at this point is we solve for y. Oops. All right, let me rewrite this y. All right, so now that we solve for y, the very last thing we need to do is actually write it back into function notation. All right, so let's write it back into function notation. All right, so what does that mean? Really, it just means to replace the y. So now I will have an equation that looks like, instead of n of x, it's going to be the inverse function. So we're going to put that little minus 1. And it's going to equal to x plus 12 over 4. All right, so now we have the inverse. All right, and that's pretty much it. So look at those steps. We have function notation, right? So we're going to change it to equation notation just by putting the y instead. Then we're going to swap our x's and y's, right? These look identical except the x and y have been swapped. We're going to solve for y, and then we're going to write it back into function notation. And there is how we write a function as an inverse function. All right, so common mistake on these is a lot of times people will see this and say, oh, I could do this without having to do any of that. Keep in mind, we are practicing with simple equations. The steps I'm showing you are designed to apply to more complicated equations. So if you try to do too much of this mentally in your head, chances are it's going to lead to some type of error. One common mistake is many times people say, oh, I get it, so we just have to switch the signs. And so a lot of times people say, oh, look, it's a plus 12, now it's a minus 12, I get it, I just have to change it. Well, it's not, right? It's not just switching that. You'll notice now we actually have a fraction as a function, whereas before we didn't even have a fraction. So sometimes you never know what the final output's going to be. And then especially if you don't do things in the proper order. So if you're not following the correct order of operations, you could end up with the incorrect function. All right, so now let's try this again. So we have this other function, j of x equals to x minus 7 over 10. Let's follow the same process where we're going to change this to equation notation, right? So equation notation, writing this out just to remind you. And so we're going to replace this j of x with our y equals, sorry, blanked out for a second. So we're going to put y equals and x minus 7 over 10. That stays the same. So now we're going to swap, right? We're going to swap our x's and y's. We're going to swap x and y. So now we're going to be left with x equals to y minus 7 over 10. All right. Now next step is we're going to solve this. Right? We're going to solve for y. See if I could squeeze this in. So solve for y. All right, so the question is, what do we do next? How do I get y by itself? So this is where a lot of times there's a common mistake. We see the y minus 10, and the easiest thing to do would be to add 7 to both. I'm sorry, we see the y minus 7, and the easiest thing to do would be to add 7 to both sides. But we can't do that because that's in the numerator. So there's that 10 in the denominator we need to get rid of. So the easiest way to deal with this is to actually multiply both sides by 10. So I'm going to put it on this step here so I could squeeze it in. Right, so I'm going to multiply both sides by 10, and when I do, I'm going to be left with 10x is equal to y minus 7. Now you're one step away from actually getting y by itself. Now we could do the plus 7 to both sides. So I'm going to add 7 to both sides. And we're going to be left with y by itself on the right side. Don't make the mistake of adding 10 and 7 together. Those are not like terms. And make sure you put your x's first. So this is going to be 10x plus 7. And that's it. All right, so now we just have to write it in function notation, which will look like, let me write it up here. So we're going to go back to function notation. And don't forget where you started. You'll notice the notation originally was use the letter j of x. So we want to make sure we continue that. So this is going to be j of x, inverse j of x, is equal to 10x plus 7. All right, oops, I didn't complete that. All right, so here is our inverse. All right. So that's the general idea of how to do this. Definitely this applies to all the different functions. Doesn't matter if it's a linear function or quadratic function, square root function. The process is the same. You're still going to write it into equation notation. You're still going to swap your x's and y's, solve for y. It works exactly the same way. All right, so the last thing I want to talk about is actually observing how these functions look on a graph. So it's one thing to understand that the numbers get swapped. Input becomes output, output becomes input. We've seen it in our equations, we've seen it by plugging in numbers, but what does that look like on a graph? All right, so here I have this equation. This is a linear equation. H of x is equal to 2x minus 1. So I have a function table already for us. So this is a table of points of x values. If I plug in those x values into that equation, right? If I take all these values and I plug it into this equation, 2x minus 1, right? Here's my h of x. It's going to give me all these y values. All right, so that's something we could plot those points and we could graph that very easily. So let's do that first. So make sure you copy down that table, and let's see if we could graph this. So I'm going to start with, this is linear. So technically, I guess technically we don't even need the points. We just need the equation. I know that we have a y-intercept of -1, right? Because according to the equation. So that's 0, -1 is our y-intercept. It says it in the table as well. And we have a slope of 2. So up 2 over 2. So up 2 over 1. So up 2 over 1, up 2 over 1. So, and then down 2 over 1. So very easily, here's all the points that are a lot of the points that are in the table that fit. So we should be able to draw a line that goes through those points. Let's see if I could do that. All right, so it should look something like this. And this is our h of x. All right, that's our equation, h of x. Now, what does the inverse look like? Now, we could rewrite this equation, but we don't need to rewrite the equation in order to graph it. So let's look at the table. You'll notice I have an inverse function table. So the reason why I have this is because I know that all the values, your inputs and outputs, get swapped. So when I look at this table, for example, the first point, -3 and -7, -3 is an input and -7 is an output. So that is going to tell me exactly what goes into my inverse function table. So all the outputs now become inputs. So all I need to do is to copy. I'm going to copy these points. So this is -7, -5, -3, -1, 1, 3, and 5. Right? All I did was copy the outputs of the original table. Well, if it's the inverse function, then that must mean all the new outputs must be the original inputs. So I could just copy those. -3, -2, -1, 0, 1, 2, and 3. All right, so that's probably the easiest. If you have a table, you could just switch the input and output, and now you have a new table. All right, so we don't have any equation. We don't have any equation for the inverse, but we do have a bunch of points we could plot. So let's just plot these points and see what it looks like on the graph. All right, so let's start with, let's see, what fits? -5, -2, 3, 4, 5, -2, that's over here. -7, -3 doesn't fit. So I'm just going to use -5, -2, -3, -1, -3, -1, -1, 0, 1, 1, 3, 2, and 5, 3. All right, so there are all the points that I could fit. And so what I'm going to do now is draw a line that goes through all those points. Should be something like this. All right, so this is our inverse function. This is our inverse function. So you'll notice it still looks like a straight line, except it's not in the exact same place. It looks very similar to the original. So the question is, what or why does it look like this? All right, what's affecting it on the graph to look like this? Well, one thing that to keep in mind is in order for us to get our inverse, we had to switch our x's and y's. So y becomes x, x becomes y. Y equals to x, x equals to y equals to x, y equals to x. So if I think about this, if I think about y equals to x, right? That really means we're swapping. So what does the equation of y equals to x look like? Well, that means for every time you plug in a number for x, you're going to get the same thing for y. So if I plug in a 1, I get a 1. If I plug in a 2, I get a 2. If I plug in a 4, I'm going to get a 4. If I plug in a -3, I'm going to get a -3. So if I think about all those points, and I draw a line that goes through all those points, then I'm left with this line that's right in the middle, which this is y equals to x, right? Because we're swapping. Don't forget, we're swapping x's and y's. This is also our line of symmetry. Line of symmetry. So if you think about it, if I look at those two lines, let me see if I could do this. If I take these and notice it might be easier if I look at it like this. You'll notice those two lines cross like an X, and that line of symmetry goes right down the middle. It goes right down the middle. So that's exactly what our line of symmetry is supposed to do, right? It's supposed to go right down the middle. So if I go back here, you'll also notice that this distance between these 2 points is actually the same. So however far it is from this point, it's the same distance to the other point. All right, same thing over here. It's a little bit closer, and it's a little bit closer, right? Even in the negative region as well. So you'll notice it goes straight across, and this is always going to be perpendicular, right? Connect these two, and it's going to be perpendicular, right? That's how we know that's a line of symmetry. So anytime you have a graph, if you know that there's this line of symmetry that cuts it down the middle, then it might make it pretty easy to graph an inverse without even having to do a table. So you'll get more into that. We'll try to get more practice on that. If you don't see it this year, you'll see more of it next year when we get more into details with inverse functions. All right, that's it for now on this lesson. You let me know if you have any questions, and have a good day.